How are you guys doing? You having fun? Well, it's Thursday. You should have, right? Because it's only one more day left. So how was your Wakulla trip? Did everybody go to Wakulla? No? Oh, good. You saw the alligator? Oh, good. Oh, really? That's good. I think I haven't seen one above water, except the statue at the hospital. Anyway, so I'd like to know who came from outside Florida. Oh, a lot. Good. Let's see, what's the farthest? California? No. Oh, one. New York? No. New Zealand. Oh, wow. That's like across the globe. Well, I came from the Philippines myself, so we're in the same part of the globe. Anyway, so who are first-year grad students? Okay, graduating grad students. Close to graduation? No? Oh, one, good. And who was, let's see, who are in physics? Almost everybody. Chemistry? Biology? Nobody? Politics? Ah, good. How about Trump supporter? Sanders? Oh, there's one there. Okay, good. Well, this NMR has a long history, and I wouldn't have time to, of course, to condense that in 1 hour talk. So we're just gonna touch the salient point of NMR. I've been doing this for almost 30 years, plus or minus 8 times 30 years of sleep. So that's 8 hours, 1/3. So that's basically the experience we have. Now, so I'm going to take you to a little bit of history of NMR first, so you can kind of appreciate where we came from. NMR is a very old technique, much older than transport, for example. No, sorry, not as old as transport. Transport has probably been before that. And you can say that NMR had been a product of World War II, because during World War II, people are using radio frequency, RF, in radars in order to detect enemy ships or installations. So most of the instruments that they use in the war had been used after the war in radio detection. And basically, NMR is a radio detection technique. So I could say that we can divide the history into 3 parts. This is totally arbitrary. This is only for my own kind of division. Most of the original techniques was discovered prior to the war, when physicists started to realize or to learn more about this new science called quantum mechanics. Right, in the 1920s, people don't know about the atoms and things like that until they found out that nucleus of the atom has spin, and that's the basis of it. And then it was followed. What's interesting in this history that I found out is that there's a lot of Nobel Prize winners in such a small niche of experiments. I mean, technique, NMR. There's at least 10 in the last maybe 80 years. And you cannot find that in any other fields. For example, it started with the Nobel Prize when Stern detected the nuclear magnetic moment in the atom. And a lot of other Nobel Prizes as recent as 2003, where the MRI had been discovered. Anyway, has anybody here inside an MRI machine? You've been in an MRI machine? So what did you notice about the MRI machine? Noise, the tick, 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 right? Those are the pulses that you apply in order to get the NMR signal, and we're going to discuss that later. And it's very loud because you have to have a lot of power in there in order to detect the signals from your body. But anyway, the point here is that most of the developments of NMR actually occurred between 1945 to around 1960 when physicists, and this is very interesting because the physicists normally during that time, they were called the nuclear physicists They are not condensed matter physicists. So they study the atoms. What they did is they used NMR in order to measure the nuclear magnetic moments. But there's only a very few number of elements in the periodic table. So once you get up to uranium, there's nothing to measure anymore. So they lost interest. And it was taken over by the chemists. And up till now, chemists and biologists are actually using MRI or NMR in order to study proteins and all body structures and stuff, drugs, for example. Now, what interests, an important discovery here that in 1949, what they found out is if you measure the nuclear moment of copper in a copper metal, and you measure the nuclear moment of copper in copper oxide, okay, they're same copper, you will find out that the nuclear magnetic moment are different. They're not the same. And that's what creates a revolution in how you can actually use NMR in order to study condensed matter physics, as well as the structure of molecules. Because it turns out that that difference has to do with the interaction of the nucleus to the electronic structure of the material. Therefore, you can study what electrons are doing by just looking at the nuclear moment, okay? And that is called the night shift. It was discovered by Walter Knight in 1949. And we're going to be studying that too later in this talk. Anyway, so after that, the NMR becomes commercialized, and there's a lot of developments in the technique. FT NMR, Fourier transform NMR, had 1992 Nobel Prize, was most of the prominent discoveries or development of the techniques. And most of these are now done by chemists and biologists. Lothar Bohr, for example, had won this MRI Nobel Prize by developing the technique on how you actually image your body. So this is very recent. But his work was done way back about 10 or 15 years before that. And recently at MagLab, we were able to do NMR at higher fields. First in 1995, where the first NMR was done at 25 Tesla here in the MagLab. And most recently in 2000, we used the 45 Tesla hybrid magnet, as Tim mentioned. And other developments include the pulse field NMR at 60 Tesla, which is done at other magnet labs, for example, in Germany and France. We don't do it here. The pulse field is at Los Alamos. But this is a very new technique, and it requires a lot of engineering and developments. So if you look at these pictures, just to show you how things have evolved, I separated this slide into two. This is the old, very like 40, 50 years ago, and this is like the modern era, the colored ones. In the beginning, the way they take data is they will take a picture of oscilloscope. And this is what typically the NMR signal look like. Whereas in the days, you have a digitizer. You can look at it in your computer, and then you get all the data there in a click of a mouse. Here, they will take days in order to take a picture, process the film, and develop the film, and then print it out. It takes a long time. And there's no Walmart back then where you can just put it on the machine and it will come out the picture. They have to really go and go to a photographer and do that. So there's a lot of developments, and you can see the old machines here, which are vintage from war. This magnet is 2 Tesla. It's a cold magnet, circa 1960s. And now we have 45 Tesla hybrid magnet and the 21 Tesla all superconducting magnet. Have you seen in this magnet back in NMR? Okay. Well, one of the most notable observation I had is there's a picture of Redfield here, who was a grad student of Purcell. He developed theory in relaxation time, and he was wearing a very nice tie. And whereas the new grad students now are like this, they will wear football jersey and the hat is backwards. So see the development, Have you ever used anyway, coat and tie maybe. So if you look at the developments of magnet we use at NMR, I divided this into four types of magnet: the superconducting, resistive, hybrid, and pulse magnet. You see this in colors. And what is notable here is the increase in the field that we can now do is almost linear. For example, in superconducting magnets, this is the maximum field, and this is the year when it was installed. And you can see the development here is almost linear. We expect that around, this is my old thing. There's supposed to be something here I changed yesterday but didn't show up. There is expected to be that in around end of this year or maybe early next year, we're going to have a 32 Tesla all superconducting magnet here at the MagLab. So this is a new development. So to give you an idea of the difference between what we do in condensed matter as opposed to ChemBio, is there's really kind of a diverging path ever since 1960 on how we use NMR in different ways. So, for example, in condensed matter, we use we study samples, crystals, like what we do, most of you do. And where in ChemBio, they study complex molecules and proteins, okay, living objects. The nuclei that we are worried about are more on metals, copper, aluminum, bismuth, most of it in periodic table. Whereas, of course, in chemistry, you look at organics, protons, carbon, potassium, nitrogen, things like that. It's very limited. So the science is focused on the electronic correlations, whereas in ChemBio is molecular structure. The spectrum, NMR spectrum that we see are very broad in the range of megahertz, whereas in ChemBio you see very narrow lines, very sharp lines. And in itself is very good because that's how you can resolve the cancer in your body when you do MRI. They can actually resolve very down below 1 millimeter resolution. Of course, for condensed matter, we have low signal to noise. And the reason for that is the abundance of the nuclei, and the gamma, which is the gyromagnetic ratio I'm going to tell you about later, is very low. Whereas in ChemBio, the gammas for these atoms are very high. So it's very high signal to noise. It's easy experiment, whereas we have hard experiment. The lifetimes of the nuclear signals are very short. They disappear quickly, whereas for ChemBio is very long, seconds. Whereas in milliseconds, it disappears. So it's like 3 orders of magnitude difference. The technique is, of course, very simple. We use maximum of maybe 3 pulse sequences, 3 pulse, and then they could have many multiple pulses. And they can have 2D NMR, 3D NMR, and all this kind of stuff, complicated stuff, which I don't claim I know, because they advance the science of NMR over many, many years. Now, of course, the difference is we do cryogenics. We go down millikelvin, microkelvin. We can do NMR, whereas most of the ChemBio experiments are room temperature. Probably if they go down in temperature, it would be like 77 Kelvin liquid nitrogen. Okay, so they don't, of course, you cannot freeze human body and then do a NMR, so it's hard to do that. So the other one is the instrumentation, of course, since we are facing very extreme conditions of temperature and fields, we have to develop our systems. You cannot buy the instruments that we use, whereas it's very easy to buy commercial spectrometers that can be used in ChemBio. So if you go to the NMR lab that is chemistry and bio related, they have very nice, nice looking spectrometer. Magnets are like a spaceship, it's like you're inside a high-tech area or something like that. But in condensed matter, we don't care. And of course, it comes with the cost. You can build NMR spectrometers in $10,000, whereas you have to spend millions in order to build a lab in NMR, in a chemistry NMR. Huh? Normally, it's the magnet. Because a high-resolution magnet, for example, if you buy a magnet that's like 10 ppm, you could probably spend $100,000 just for the magnet. Now, the chemists, because they wanted a very high resolution, is 1 parts per billion. And for every order of magnitude that you increase the resolution, you're going to double the amount, the price. So, you know, the magnet could cost you up to $1 million, just the magnet itself, if you go to 1 parts per billion resolution. It's a good question. Okay, so if you're a grad student, you may want to ask, if I'm going to do NMR, where I'm going to go? You know, what can I use this knowledge for to get a job? Well, there are actually a lot of options for you for NMR, and this is not very obvious to a lot of people. But there are a lot of application in industry, and most of it, as you know already, is MRI. There's a lot of companies that build MRI machines, okay? And if you know the details about that, most of that is done by engineers. But if you're a physicist, you're more equipped to understand the details of NMR and improve it. And I have 2 or 3, 4 colleagues that had gone into Siemens and GE that build MRI machines, and Philips. And they're involved also with the development of brain scans. And they're really more knowledgeable than I am in the MRI business. And there's other things that I listed down here. For example, petroleum. Of course, oil is getting cheaper now, and the oil companies are getting bankrupt. But NMR is very important in testing. For example, if you have oil-bearing rocks, you would put NMR probe into the earth and use the Earth's magnetic field in order to do NMR. And then the signals that you get depends on whether that rock can hold oil or water and things like that. And you can study that. So, yes? How do you determine it? Yeah. Well, what NMR does is, I'm not in this field, but as far as I know, and I'm working with some colleagues that actually had funding from oil industry, in fact. They look at the 4 sizes of rocks. So there are rocks that are large cavities, and there are rocks that are low cavities, small cavities. And some of them, they know that they can bear oil, and some of them, they don't. And so what you measure is what we call T1. And T1 depends on the size of the holes. And then you can find out the porosity of the rocks. Yes?
So as I understand, then you do MRI instead of not the normal measurement, so like the proton NMR or carbon NMR, right?
For MRI, you can, normally it's imaging, for imaging.
Yeah.
You actually look at protons because human body have a lot of protons, hydrogen, right? And proton turns out to have the largest NMR signal in the entire periodic table. And I have not seen any other MRI using other nuclei because they are much weaker. At least the next strong intensity NMR signal in the periodic table is fluorine, but you don't have fluorine inside your body. Teflon maybe, but not inside your body. Go ahead. It's okay.
The last question, comparing the FTICR mass for the detecting of petroleum, what's the advantage of NMR to analyze the petroleum?
The FT-NMR is simply a technique. So it's just making your signal acquisition faster than, normally that's what we do. Once it's discovered, almost everyone that I know use FT-NMR. MRI is simply imaging, but it also uses FT-NMR. Oh, of course, it looks at different ways. In petroleum, let's say FTICR, you're looking at the distribution of mass. Like, for example, there's big molecules and small molecules. But NMR is not looking at that. It looks at the nucleus. It's like comparing what's the advantage of transport versus NMR. You're looking at different things. Like you're looking at a box and you're using different technique in order to study the box. And so I wouldn't say that there is any advantage much, there is a difference in what information you can get from the experiment, but they are not necessarily more advantageous than the other. They give you different results, okay? It's like, you look at your food and you say, is this tasty? You can smell it or you can lick it. So, all right. Well, one of the things I want to emphasize here is that a lot of people go to pharmacology because NMR allows you to determine the structure of drugs. And you can even do designer drugs in order to specifically target a disease. And this is one of the things that chemists do. Of course, quantum computing is a new thing that allows you to measure using nuclear spins as qubits. You can do quantum computing. So just, okay, I have to kind of go faster here. So NMR is only a tool for us. And the reason for this is important NMR in condensed matter is because you can actually study the local structures, meaning that if you do transport, you have to put current into it. So you invade the sample because you change the condition of the sample. And you're only looking at the bulk, the entire response of the bulk. But NMR looks at a very specific site in the unit cell in the crystal. For example, if I just want to look at copper, you want to look at vanadium or whatever, or bismuth, whatever is the atom in your system, you only look at that specific spot. You don't look at the entire sample. Although, of course, it's an average over the entire sample, but you can pinpoint. That's why it's called local, okay? And very site-specific. And as I mentioned, it's not invasive. It has very, very low energy. In the MagLab, we also use simultaneous transport. We also do magnetization at the same time, or dielectric, or optical at the same time as NMR, so you can study both at the same time. And there are some other related techniques that are related to NMR that I put out here. So, it's very, yes?
Is there any way to have a spatially resolved NMR, say from a small pickup?
Yes, yes. That's the basis of MRI, basically. That's how MRI can image a particular part of your body. Yes. So there are more than 100 naturally occurring NMR nuclei that you can actually study. So the question for you is, there are only 92 naturally occurring elements in the periodic table. Why do we have 100? Because isotopes. For each isotope, for each element, you can have, for example, for hydrogen, you can have 3 isotopes that are NMR active. Okay? Proton, deuterium, and tritium. They're all NMR active. So you can actually separate them and look at them individually if you have those in your system. Now, there are other systems here. There's, for example, copper has 2. Copper 63 and copper 65 have different signals. And then you can actually, if you look at your sample that has copper, you can look specifically at copper 63 or copper 65 separately. So here's the basis of all this. Why is it important in condensed matter? It's because what we call as hyperfine interaction, okay? You think of a nuclei which is in there, and then the electrons are going around, right? Now, the fact that the electrons are going around the atom creates a magnetic field into the nuclear site. And that's what makes the NMR like a spy. It looks at what the electrons are doing. So if you have an ordered system, you have an antiferromagnet, that electrons will order. Once they order, they create a magnetic field in the nucleus, and then the nucleus will see that. And then you can see that the NMR spectrum is going to shift and due to that local field. And this is what you call the hyperfine interaction. That energy is very small, 10 to the minus 6 eV. So it doesn't really, the electron doesn't feel the presence of the nuclei. It doesn't change your system, except the electron, the nucleus is actually seeing what the electrons are doing. So if you look at this phenomena, you can look at this book. Schlichter, Abraham, they are the basic, in Fukushima for more of the hardware. So the way you look at, this is the basis of NMR, is you have a nucleus that is any atom in your body or any atom in the universe is subjected to magnetic field. And what is important, that is subjected to magnetic field, will create a nuclear magnetic signal, NMR signal. Now the only problem is how do you actually detect that signal? So if we start out with the fact that the nucleus has a magnetic moment, you can see that the Hamiltonian of that system is going to be the moment multiplied by the field. Remember, you have to have a field, okay? So the magnetic moment is U. I is the nuclear spin here, I. So I, why do we use I for nuclear spin is because we think of the spin as current, and I is a symbol for current. So why is I a symbol for current? There's C is current, come on. Nobody thought about that. Okay, so when I think what happened was when Ampere tried to formulate the force between two current carrying wires, he already used C for charge. So in order to create a symbol for current, he has to invent another symbol. So he said it's an intensity of current, so it's an I. That's where it came from. So why is H field? Anybody? It turns out, this is what I saw in, of course, you can see this internet, that when Maxwell's equation was written down, he can only use letters from A to G to H. A is the vector field, B is the field, which is another question why B is field, and then H is the last one. But anyway, that's historical. All right, so let's look at what happens to nuclear spin as you put it in magnetic field. So basically, this is like a spinning top, okay? When you put a spinning top in Earth's gravity, there will be a torque coming from gravity. And because of that, it will precess around, the top will precess around the an axis, right? The same thing happens with nuclear spin. And so when you put a nuclear spin in a magnetic field, it will precess in the same manner. Okay, this is just mechanics. Now, the precession of frequency is called the Larmor frequency. And this is the basis of all NMR. So this is the natural state of any atom when you place in magnetic field or nuclei. And that range, the frequency range of that precession falls between kilohertz and gigahertz, which is in the radio frequency range. That's why we're using all instruments of radio, radio frequencies that we use in World War II. And of course, even cell phones uses the same range of frequency. That's what we get the signal from. And in fact, the instrumentation for NMR is basically cell phone technology. So you can do a quantum mechanical treatment the same way. The time derivative of the nuclear spin is a commutation with Hamiltonian, and you can work this out. At the end of the day, you get this equation, which is the same equation that we got earlier. This is the precession frequency. So if you look at different atoms that has different spins, for example, proton H1 has spin 1/2. I didn't emphasize that, but if you look at this equation, this is a very important quantity called the gyromagnetic ratio, because this defines essentially a fingerprint of that atom, okay? Each atom or each nuclei has its own fingerprint. So gamma is a constant only for that particular atom. That's why we can identify which atom resonates at which frequency because of this gamma. So if you look at this, for example, for copper, you see copper 63 and copper 65 have different gyromagnetic ratio. And if you compare copper 63 and oxygen 17, you see that they are twice as big, right? Almost 5.7, 11.2. And so you expect that the oxygen is going to precess twice as slow as copper. And by knowing that frequency, we can actually see, you can actually guess what nuclei are you looking at. So here's the periodic table again, and if you look at this is what we had at MagLab. You never see this in any world because anywhere in the world because we produced it here. There is a gamma, for example, this is potassium, specifically to tell us that that's the fingerprint of that particular atom. So this is specifically a NMR property table. So how do we produce a resonance condition? So imagine this. What do you mean by resonance? Anybody? When do you say we have resonance? So when you have something that is naturally oscillating, for example, a child on a swing, okay? You just do that. And you want to, for example, amplify the amplitude of that swing. You have to put a force to it. But you have to put a force that is the same oscillation frequency as that swing. Because if you push the swing while the swing is away from you, that's not going to work. You have to push it whenever the swing goes back to you. So the frequency of the force has to be equal to the frequency, the natural frequency of the oscillation of a body. That's essentially the same thing as in NMR. So we had a resonance condition that has to be fulfilled because there's a natural frequency for the nucleus to oscillate in the magnetic field, which is called the Larmor precession. Okay? So, for example, if the nucleus is spinning like this and we want it to be bigger, we have to apply that force that follows that. Okay? In order to do that, so we have a magnetic field up. So how do we gonna make it like this, right? So if you imagine we apply a magnetic field this way, then the total field now is a vector sum of that field up and field this way. So now instead of precessing that way, it will go this way. You follow? Okay? So what we want to do is to maintain that orientation that we're going to tilt the field by adding additional field. But since it's rotating, we also need to make that horizontal field going and following the spin, because otherwise it will be just pointing this way, right? So we have to do that. And this is where the concept of instead of a magnetic field that rotates, which is very hard to do, because then you have to have a rotating magnet, right? And that rotating magnet has to be megahertz, 1 million times per second. You can't do that. So instead of doing that, we're going to create a field that's linearly polarized. It's not rotating, but it's only going this way. But of course, that's just the same thing as rotation, except we're looking only at the one orientation, X or Y, it doesn't matter. Okay? In order to do that, so here's an animation of doing that. Here's the magnetic field, and this is what we want to do. Of course, this is only a component of a magnetic field that's actually rotating along XY axis. In order to produce this, all we got to do is to make a coil oriented such that the magnetic field coming from this coil is going perpendicular to the magnetic field that we apply, which is the magnet itself. Okay? So if we apply an oscillating magnetic field, which we call H1 here, then we fulfilled our condition. So here I will introduce to you two concepts. One is the lab frame and the rotating frame. So if I were a nucleus and I was doing this, if you're observing the nucleus, you see me going like this. But if I'm riding with the nucleus, okay, right? For me, I'm only this. I'm not moving. It's just like this because I'm riding with it. That's the rotating frame. Okay, the lab frame is where you see this, because if I rotate myself, you see me, I'm rotating. The spin is rotating. So this is what it looks like. So So what's going to happen is now if I'm applying the magnetic field that's rotating here, then for me, the oscillation goes like this. Okay? Where for you, it's going like this. Okay? So that's a rotating frame. For me, I'm on the fixed frame. I'm only seeing going down. And that's what this is. Okay? That's the difference in the rotating frame. Now, you can make beautiful pictures out of this, because if you think about it, if you draw the tip of the vector, okay, the tip of the spin vector as a function of the increasing H1, increasing magnetic field, and so this is the picture. As you can see, that you can start like this, but if you make the H1 field bigger, you can have big change, okay, in a short amount of time. So as you increase this, you can form these beautiful pictures from very, very fine oscillation to very rough oscillation. And you can even make it so big that in one fell swoop, you already go 90 degrees from, or 180 degrees from the direction of the magnetic field. And you can go see something like this. This is on resonance. And if you are on off resonance, you can also do the same thing. Except since you're not resonant, you're not going to be able to flip it large angles. So you go like this. At a point that you have matched the frequency of the H1 and magnetic field, you go back. Then you go back again. So off resonance, the spin is actually rotating like this. And that's this picture here. And if you increase the H1, you could probably go like this and then go back. But you're never going to go to the other orientation where you have a very a nice oscillation like this. Okay? Because you're off resonance. That means you're pushing the swing not in resonant as the natural swing of the frequency of the swing. Okay, so if you look at the quantum mechanical description of this, this is so easy to look at, to figure out. If you have a spin 1/2, for example, in this case, you will have two energy levels when you put in magnetic field, up and down, -1/2 and +1/2. In quantum mechanics, all you're doing when you flip the spin, you're actually changing the energy from up to down, or down to up. In this case, you're increasing from m equals +1/2 to -1/2. And since this is not the natural state, the population of the upper energy level is going to go down to the lower energy level, and that will emit energy. If you can detect that energy, that is the NMR signal. Okay? And what is that energy detected as? Okay. This is when it's at resonance. So when that frequency is the same as the difference between these energy levels, then you have a resonance. If the frequency that you apply is not enough to enable excite the population from lower energy level to upper energy level, then you will not be able to achieve resonance. So you're off resonance in that case. Now, the signal that you actually get from NMR is very, very tiny. Normally, it's tens of microvolts, very, very small. So you have to amplify it to more reasonable level, like a volt, so which is 1,000,000 times, okay? And the reason for that is if you look at the Boltzmann distribution of the population in this case, the difference between the upper energy level and the lower energy levels, like at room temperature, is like 1,000,000 times, 1,000,000 of the number of populations, so 10 to the -6. So the ratio of the frequency to the temperature is very small. So that's what makes NMR very difficult in that sense. But there are a lot of techniques which I'm not going to be able to cover. So this is the experimental setup that we use in the MagLab. You have this sample, and then you have a coil. And the actual, this is the magnet in cell 2, for example, the resistive magnet that you saw in your trip. So this is the probe that we use. Let me see if I don't have it right there. So close up of the probe, we have the NMR coil right there. This is in a goniometer. that allows you to rotate the sample in 2 directions. Now, if you look at MRI, MRI is the same way, except the sample is a human body, and there's a big coil. But the magnet is actually horizontal. Okay? So if you look at it, this is the sample, and the coil is like here. Okay? So in order to do that, remember, we have to make the direction of magnetic field perpendicular. So it's very hard to make a coil which axis is along this direction to have the magnetic field pointed perpendicularly. So you do what you call a saddle coil. So you do like a Helmholtz coil. And you put the sample inside horizontally. So this is basically what you see in the MRI setup. So we had a sample like this in our lab. We recreated this kind of thing. There's 2 coils here, and there's a sample. All right. So how do you observe this resonance? So the technique is what we call pulse NMR. So when we apply an H1 field, we only apply it for a short period of time, just enough for the spin to go 90 degrees. And then we stop. Okay? And then we'll let it sit there. Okay? So instead of doing this, it will be doing this. Now, why? Because the way you detect the sample is you also use the same coil that you use to flip it. So when you flip it, you apply a big magnetic field on the coil. Now it's flipped, and now you stop. Now remember that the magnetic field is created by the nucleus itself. It's a magnetic moment. So it's like a bar magnet spinning around on the XY plane. And then the coil is in there, so the coil will detect a spinning magnet, right? And that creates a voltage. That's what NMR signal is. So if you look at the picture here, here's our H1 pulse along the x-axis, very, very short. And now this is the magnetization that on the z-axis, it goes down because now we start with z-axis and then we go to the xy plane. It goes to 0 right after the end of the pulse. But at the same time, the magnetization component along the x-axis is building up right here while you're pulsing, because now you're getting more component along xy plane. And then you stop pulsing. Once you stop pulsing here, this signal continues to precess and still generates voltage. So this is the signal that you want. In the lab frame, it looks like this. So first, let's wait. You start, so now you see this, and then it's on XY plane, it's on, just stay there. Whereas in the rotating frame, it's just stuck in one direction, because for me, it would be like this. Okay, I'm only in one direction. But for the lab frame, you see it's precessing. Now, this requires a large amount of power. So this amplitude here is in the order of a kilowatt, or about 300 volts, in order to create that precession, a big, big amount. And you only use very short time. So this is the order of microseconds, this pulse width. And I will show you in the lab practical how it's done. Now, what happens in reality, that's the ideal case. What happens in reality is that there is interaction between the nuclei themselves. So the nuclei are not going to do that forever. They actually decay. And the reason is we're not only talking about one nuclei, we're looking at 10 to the 23 nuclei. There's a lot of them, okay? So actually, that signal that we saw constant is actually decaying. And so instead of seeing flat here, you actually have a decay, and this is what we call FID, right there. It will decay instead of going constant. And the reason for that is the nuclei, if you separate them into different components, will actually cancel, because some are moving faster, some are moving slower. And so the average will go down to 0. Okay. Yes? It will. I will go there. That's a good question. Now, there are some problems sometimes in electronics, especially in condensed matter. Not so much for biology, because for chem bio, this signal that we saw earlier actually extends to seconds, very, very long. But in our case, sometimes this signal is very short, microseconds. And the problem here is that depending on your electronics, you're actually putting a 1 kilovolt pulse here, and yet you're detecting a microvolt pulse, a microvolt signal. And it's using the same coil. So that means that whatever is what you use for amplification of that small signal is what you use for putting a large signal. So you could think that the amplifier is going to be deaf at that time. It's like you're ringing a bell in the tower and then you cannot hear anything because your ear is all saturated with noise. And therefore, your amplifier is not effective in amplifying a small signal. And it will take time in order for it to recover, and that's what we call a dead time, called electronic dead time. So the signal is actually not amplified at that point, okay? And so, therefore, we cannot get any NMR signal. So what do we do? And this is invented by my academic grandfather, Erwin Hahn. He's from Berkeley. He was a professor of my professor, so I'm the grandchild. And he invented what you call a spin echo. Okay. And this is a complicated way of looking at it. There's a video on YouTube or on the Wikipedia, I think. This is what happens. What you do is you do two pulses. One what we call 90-degree pulse, which flips to 90 degrees, and then you flip it 180 degrees. And you can see all the spins are going 180. And then because they are precessing in field, which is along the z-axis, they will recombine at some point and form what you call an NMR echo. Okay? One way of looking at this is what a racetrack analogy. So if you look at a racetrack, for example, like say people are lined up in the beginning, and they said, okay, start. But whenever you hear the second bang, you have to go back. So the first guy who went around, which is ahead, is now going to be the one that's behind. And at some point, they will come back to the original position. That's what you call the spin echo. All right? Now, if you look at the NMR electronics, it's really simple, and it's really, it's like a regular cell phone. I will show you later. What happens is you have to have a frequency source, and you have to generate a pulse, and then the sample lies here where L is. There's an LRC circuit, and then you have to detect that. I don't have time to cover the detection part where you have to have some kind of a radio heterodyne or super heterodyne or homodyne system in order to, you know, how you detect a radio. But I will explain that during the hands-on. And if you look at this, this is like the cell phone. Okay, the NMR signal is the signal from your cell phone, which is very weak. It's the tower transmit, and then the NMR signal will come here, and then will be received by the tower. The same thing. And all the electronics are basically based on cell phone technology. All right, I'm running out of time. 10 minutes. So in the MagLab, we have many different instruments that we use for users and also for our own research. And I think you're going to have a copy of this. I'm not going to have time to discuss this, but there's different ways that you can combine, for example, resistively detected NMR and optical pumping and things like this. So it's more than just a garden variety NMR, but also combining with different techniques, pressure, for example. Now, this is the picture of a typical spectrometer. We put it in a cart so we can carry it over there because our lab is over here about a quarter mile away, so we have to push that. It includes everything from temperature controller to network analyzer and synthesizer. We're going to cover this in the practical later. I'm going to show you. And this is our software, which is written in-house also. The magnet systems you saw already in your tour. The hybrid magnet, cell 2 is what we use. It has a very, very high homogeneity, less than 4 ppm per millimeter. And we have also a magnet in our lab, and also we use the dilution refrigerator to go down to millikelvin in order to do the NMR. So one important aspect of NMR that is very useful in condensed matter is called the quadrupole interaction. And this is where, for example, you can detect if there is any structural change. For example, if the symmetry of the crystal changes, then the arrangement of charges in the system changes, and the nucleus is going to see that. All right? And this has to do with the shape of the nuclei. Some nuclei that are not spherical, any nuclei that has a spin greater than 1/2 will have a non-spherical shape. And because of that, the charge distribution inside the nucleus is no longer uniform. Okay? For example, you can have a nuclear shape which is prolate, like a football, or an oblate, which is like a bloated Christmas decoration. I don't know how to do that, but some people call it pancake. It's not pancake. But it's like, you know, this balls, and you squeeze it from the top and bottom. You see this oblate spheroid. But anyway, because of that, sorry? Ah, good idea. Pumpkin, squash. All right. So because of that distribution, it interacts with the electric field gradient surrounding the sample, which is produced by the electrons. And therefore, that influences how the nuclear energy levels are arranged. And you can detect that using what you call the NQR, or nuclear quadrupole resonance. But remember that you need a spin that's greater than 1/2 in order to see this. Now, if you look at this energy diagram for pure NMR, for example, let's look at this first. This example is particular for ice 3-hab, spin is 3-habs. You have 4 energy levels, and each one of those you can induce transitions, and they have the same spacing and therefore only one frequency. Now, if you add quadrupole resonance, quadrupole interaction, the spacing becomes non-uniform. This one will go up, this one will go down, this one will go down, this one will go up. And therefore, the spacing, the energy spacing between these levels are different. In NMR, that means that you will have 3 lines, one corresponding to each one of these. And then the center one is the same as this one, same level. So this center one is the same as that, whereas this 2 corresponds to the lower frequency and one in a higher frequency. Now, if you remove the field completely, the 3-habs, plus or minus 3-habs, and plus or minus 1/2 are actually degenerate. So you only have 2 energy levels. So in this case, you will only have one single line. But this frequency is much lower than the frequency that you see here. Okay? And I will show you an example if we have time. And I think only 5 minutes, but you can do, this is 0 field. The NQR is 0 field, but you still can see NMR that way. Now there's another, you don't have to, this is not to be confused with what we call ferromagnetic NMR, in which in ferromagnets, your spins are already producing its own field. You don't need any external field. So that field is what the nucleus see. And if it's very, very large, the nucleus is going to spin with that field. Okay, it will precess around that field. And then, therefore, you don't need any external field in that case. So going back to this picture, there are 2 ways that we can actually detect NMR. And remember, NMR, on bottom line of NMR is you're looking at the local magnetic field that the nucleus is seeing. So if that local field is produced by electrons or by external field as a magnet, it sees them all. Okay, everything is included. And there are 2 effects on this. One is called the night shift, which I mentioned earlier. It's a static effect. Because of that extra field, the nucleus is going to resonate at a different frequency. And one is dynamic, what we call T1, which is the question posed earlier. So let's go through quickly the night shift. Instead of finding a signal somewhere in frequency space, you will see it's shifted. That's because the resonance is due to the other field. So if you write the equation earlier, omega is equal to gamma h naught, we're going to add a factor here, which is expressed in percent, which is the change in field in the resonance frequency divided by the frequency that you observed it. So in a sense, when you plot the frequency versus the magnetic field, instead of a slope which is gamma, you will have a different slope. which is due to the extramagnetic field. So for example, in metals, you will have different night shift, very, very small numbers for lithium, sodium, up to lead. You can see that the night shift is very small. The bigger the nucleus, the bigger the night shift. The reason is you have bigger overlap area between the electron and the nuclear radius. Okay, let's just skip that. The other one is dynamic, so we measure T1. Now, what happens in T1 is here's a picture of how you measure T1. T1 is an energy conserving process in which once it's on the XY plane, because of the interaction with electrons, it wants to go back to equilibrium. And the equilibrium is going back to straight up, okay? And we can measure that too. This is the basis for MRI. In MRI, you actually measure T1. Okay, so for example, the T1 of the protons in the bone structure has a lot of interaction with the electrons. That interaction causes T1 to be short. Whereas in the blood and soft tissues, the interaction is low. There's not much interaction because their atoms are very far apart. And therefore, T1 is long. So by putting a color code or grayscale on the T1 value, you can assign white to a short T1 and black to a long T1, and therefore you can have a picture of, an MRI picture. This is basically what happens. So this is the cartoon of what you do. You flip it on the y-axis, and then you measure when it goes up. And how you measure it, you do it in steps. For example, you apply a pi/2 pulse, and then you wait a little bit, and then you can see that the signal goes smaller. And that, okay.